So how to do polar area with calculus? The first thing we need to do is just figure out what the idea is going to be here. All our idea of like little rectangles, Riemann sums, that's not really going to apply here because that's definitely not like thinking polar. So let's just say we have some polar curve, who knows what it looks like, some kind of lumpy thing that goes from theta equals 0 to theta equals pi over 2 here. How are we going to divide this up? If we're thinking polar, we should be thinking really in terms of r's and thetas. So in the same way that we took a little rectangular sort of slice of a regular curve, I'm going to take a polar slice of this. So here's a little polar slice where I have r here and a little itty-bitty theta in here. Now, what kind of shape is that? There's a couple ways you could do this, but the one that makes the most sense is to say, well, if theta is sufficiently small, this is basically like a really skinny slice of pizza, right? And the crust might not be perfectly like a part of a circle, but just the same as when we did our rectangles, the very top of that rectangle wasn't perfectly flat, right? But if I take more and more slices and let the number of slices approach infinity, then certainly we can approximate these as little tiny slices of circles. So what's the area of a little slice of a circle? Well, you've seen this before. I don't know when you would see this, in pre-calculus or maybe in Algebra 2. But if you have a sector of a circle of radius r, and you want to know the area of this sector, you can set that up. You can figure out what that is really easy by setting up a proportion. So the theta here, how much of the circle do we have? Well, I've got theta out of a total of 2 pi. Right? So for example, if theta happened to be pi over 4, that looks kind of pi over 4-ish. If theta was pi over 4, then I would have 1/8 of the whole circle. Right? I'd have pi over 4 over 2 pi. That's 1/8. So whatever portion of the circle is, this fraction right here represents that amount of the circle. And then I want to know how that translates to the area. So the area of my slice I don't know, but that's out of a total. The total area of the whole thing is pi r squared. And if I simplify this, or cancel the pi's and then solve for area, you can see that the area of a sector is equal to 1/2 r squared times theta. And that's what we're going to use here. So the area of this little slice is 1/2 r squared times theta. But if I let the theta get smaller and smaller, just like the x's got smaller and smaller in our rectangles and turned into dx, that differential, same thing's going to happen here. And I'm going to get that the area of a polar curve from some angle theta 1 to some other angle theta 2 is equal to 1/2, which is a constant, so I can put it on the outside, r squared d theta. And this formula looks like this because of this. Why did the theta turn into a d theta? Because we let the number of slices run off to infinity, so the angle became that infinitesimally small, that differential d theta, just like it did with our Riemann sums when we ended up with the integral of f of x dx, where f of x was the height of the rectangle and dx was the width of the rectangle. So that's it. That's how we do it. In practice, there's a couple different ways that this can happen. I mean, there's very basic examples where you just have to figure out what where you're going from where to where. So I'll give you one, let's see, in a couple videos ago, I think maybe in our polar review, we looked at this, right? And that was that thing that's, I think, called a limacon. And I'm so sorry if that's wrong, but I really don't care about the names of them that much. That's terrible to say, but I just don't. So that looked kind of like, let's see, it crossed here. It was at 1, so it went like this, and then in like this. Right? So there's different things that we could ask about this. We could say, what's the area of, we could do like different kinds of shaded regions. So we'd say, what's the area of, let's say, this shaded region? Notice that I shaded right through that. So we got to figure out like where we're looking there, right? So that's looking from theta equals 0 to what we get when we look straight up here. That's at theta is equal to pi over 2. And if I wanted to know about, well, maybe I'll leave that for a minute. So let's just do that. We'll set that up. So this shaded region is equal to 1/2 times the integral from 0 to pi over 2, those are my angles, looking from 0 to pi over 2, of r squared, where r is this, right? R equals this, d theta. And using trig substitutions and other kinds of tricks, well, mainly trig substitutions, you can actually do this by hand, but it is quite unpleasant. So I'm not going to make you do a lot of that. We're going to be interested more in setting them up, and if we need to get a value, we'll get out the old calculator. So you could try if you want to, but you can, if you see what's going to happen here, when we FOIL this thing out, which we would have to do, a U substitution isn't going to work because I don't have the derivative of what's inside hanging around here. When I FOIL this out, I'm going to get a cosine squared in there. So I'd have to use some kind of trig substitution to get the cosine squared out of there. And that is the trick. So I'm not going to do that. All right, that's finding the area of that shaded region. What about the area of this thing in here? So that's a little tricky here because I need to figure out what the thetas are when it's actually making that part. So when does it come in here and equal 0? And then as I go out, and then when does it come in and equal 0 again? So the theta 1 and theta 2 are when the r is equal to 0. That's when it's coming in here for the first time to 0, then it goes back out here, and then it comes back in again to 0. So how do you figure out when r is equal to 0? Well, you set this equal to 0. So I'm looking for the values of the cosine function where the cosine of theta is equal to 1/2. So that's happening at theta is equal to pi over 3, 2 pi over 3, and I want to run this forward, right? So I need to do the next one in front of that, and then 4 pi over 3. And I'm so sorry to tell you that you do need to be able to do that without a calculator. It's, well, something you need to know how to do without a calculator. So that means the area of this little bit in here is 1/2 times the area from 2 pi over 3 to 4 pi over 3 of same expression, r squared d theta. That's the expression. I want you to be able to write that. I don't know if you want me to maybe just really quick talk about how you recognize what those values are. So you're thinking unit circle, and you're thinking, where's cosine, which is the x value? Where is that equal to 1/2? Negative 1/2 rather. So that's here and here, right? Those are the values. So you think, you just have to figure it out from there. But I don't know what else to tell you. You need to know your unit circle stuff. So if you need to review that a little bit, then do that. All right, so that's fairly straightforward. There's only one curve. And there are some problems that we'll run into where there are two polar curves. So I'll do a couple quick examples. And there's two different ways that we have to do areas. And again, the way to determine which one it is by thinking polar. So this will be a double example again. We'll do two different regions here. Let's see. I thought of the example that I wanted to use. Let's see if I can remember. So let's say we have the two polar curves. R equals 1. And remember, that's just a circle with radius 1 centered at the origin. Ooh, that's a pretty good one. And R equals 2 cosine theta. So this is also a circle. R equals 2 cosine theta. When you plug in 0 here for theta, you get 2. So when you look at an angle of 0, you're out at 2, and then it comes around this way. So it's also a circle of radius 1. That's not as good a circle. Okay. So we're going to try to do two different areas here. Areas that are defined by not one or the other, but both of these curves. So the first area, let's do this area here. So this might be described, and these things are often described as the area, if we call this R1 and R2, area inside R2 but outside of R1. So it's all the area, everything that's inside R2 but also not in R1. So here's R1 and here's R2. So everything that's inside here but not the stuff that's also inside here. So that makes this little sort of moon shape here. Okay, so if we think polar here, you start think about what those slices look like. It's just, each slice it's the slice defined by this one, right? That's like the outer crust of that slice of pizza. And then minus the slice on the inside. So we just need to go through and find all the slices and do out the whole big slice defined by this one minus the slice defined by this one. So that's 1/2 the integral of the outside one, 1/2 r squared d theta, minus, and so the limits are going to be the same here, right? I'm going from, well, we'll do that in a second, but the limits are going to be the same, minus the first one. And notice that those are getting squared separately. They always will be. Unlike other kinds of areas that we did define by two curves, like f and g, for example, these are always separate. Where we saw some examples, like when you had those cross-section problems, where those would be inside the same set of parentheses. That is not going to happen ever with polar curves. Always separate. So that 1/2 belongs to the whole expression here. Now the question is, from where to where? So here we got to think polar again. I'm starting looking here, and I'm ending looking here. Now, what are those angles? Well, those are the angles where the two curves intersect each other. So where do they intersect? Well, they intersect when the r's are equal to each other, right? When the r's and the thetas are equal. So that means just like to find the intersection between two curves, we set them equal to each other. So that means 1 would have to be equal to 2 cosine theta, or in other words, cosine theta is equal to 1/2, and that happens at theta is equal to pi over 3. And then what should we call this angle? You have to be careful here. You could say, well, that's 5 pi over 3. But if you go from pi over 3 to 5 pi over 3, like thinking polar, that means start here and go this way. This would be cranking up through all those positive angles to 5 pi over 3. That's not where I want to be. I don't want to be on this part of the circle. I want to be over here, right? So I need to do from here to here. So this, I have to use the negative pi over 3 version of that angle to pi over 3. Not an option. You can't just run it backwards either. If you're saying, oh, well, I could just go from pi over 3 to, I could go from 5 pi over 3 to pi over 3. That will not, that'll give you the negative version of this area over here, right? Going from 5 pi over 3 to pi over 3 is this way, not this way, right? Because 5 pi over 3 to pi over 3 implies those numbers are getting smaller going this way. So you got to be careful with that. Here's another way to do it, which I think I like even better. By recognizing the symmetry of this, you could just say, hey, the area that I'm looking for, that whole moon shape, is just 2 of these, because the top and the bottom are symmetric with respect to the x-axis. So I could do 2 times, and then do 1/2 r squared d theta for the top half, and the top half is just 0 to pi over 3. And you never know. I mean, you could imagine like a multiple choice question where you have to recognize that there's sort of an equivalent thing by doing this symmetry of, and then the inside expression would be the same. Can you see all that? Yeah. So there's 2 choices. Again, not going to make you do those by hand. Just need to know how to set them up and evaluate with calculator if you need to. Quick question about that. Would you have to be in polar mode to evaluate this with your calculator? What do you think the answer to that is? You think about it while I'm drawing this. I'm just going to redraw. I'm going to use the same functions here, or curves, but I'm going to do a different area, so make a new version of it. Well, I tried. Okay, so same one, r1 equals 1, r2 equals 2. Do you want to know the answer to that question? You don't have to be in polar mode, because once you have the integral set up, the calculator doesn't care what you name your variable, so you would just put this integral in, or this version of it, with x's here and here, and doesn't need to be in polar mode. You most certainly need to be in radian mode, right? But you do not need to be in polar mode. You only need to be in polar mode if you're graphing polar curves. All right, so what about this area? So how would that be described? That would be the area inside both R1 and R2, right? It's the overlap region. It's inside both. Okay, so this is a little trickier. So let's imagine, let's think polar here. So I'm looking this way, and as I look out my different R's here, it looks like I'm just the area, like all my slices, they're just really slices of this pizza, right? This curve's not even involved in those. Slices of this one, slices of this one, up until I get to here. Right, so from here to this angle, and we already know that that angle is pi over 3, so from 0 to pi over 3, I'm inside of this circle. Let me just draw that region. I'm going to blow that up a little bit here. Geez, that doesn't look like pi over 3, does it? But you get the idea. And then there's a sort of bump up here from the other curve, right? So from 0 to pi over 3, I'm just inside of this curve, which is the R1 curve. And then the rest of the way, for this other little sort of extra crusty thing stuck onto the side of this, I'm inside all those regions. Those are inside going out to this circle, right? And they're funny shaped slices, but remember, if you let d theta get smaller and smaller, or you let the theta get smaller, we can still approximate them as funky little pizza slices, like this, and then this one, and so on, right? And as the d theta goes to 0, they will be fine approximated as little slices. So how do we do this? So from theta, oh dear, there we go, theta equals 0 to theta equals pi over 3, we're in here. And then here, from theta equals pi over 3 to, like, what's this? When does this curve get back to 0? Well, that's going from theta equals pi over 3 back to looking up this way until you're actually looking straight up at pi over 2. That's when it's equal to 0. You can check that real quick. That pi over 2 is what makes this equal to 0. So I'm going from that to theta equals pi over 2. And if you're looking at this thinking it doesn't look like it gets to pi over 2, it's because it's getting smaller and smaller as it gets to pi over 2. We are still looking up this way. It's just as we look straight up, that's when it comes back to 0. And it's not until then that it comes all the way in. Okay, so this is just two different integrals, right? It's just the area of this one from 0 to pi over 3 plus the area of this one from pi over 3 to pi over 2. And that's it. That's how we set it up. So that area is equal to 1/2 0 to pi over 3 of the area inside the first one. That's R1, which is just 1 squared d theta plus, notice that I cannot put these inside the same integral because the limits of integration are not the same. Pi over 3 to pi over 2, and then that's inside the other curve. That's this one. And again, that's what I would be looking for. I'd be looking for you to set that up and not solve it. Also, if you're remembering the way that we can combine integrals of 0 to pi over 3 and pi over 3, that isn't that just this to this? But you can do that if it's the same thing on the inside, right? So I can't combine those in any way. There's no simplifying to be done or consolidating of those two integrals into one. Can you do it? And that's that's how polar area works. It's a little bit, it's a little tricky at first, I think, but if you really try to think polar, you can do it, and I think it makes it less challenging and more intuitive. And it's kind of cool the way we can generate these areas. Now you think about like what we would have to do to try to make this into like an XY problem. It's really not pleasant at all. These problems, I mean, these particular kinds of regions are just so much better described in polar equations, and the calculus is much better that way. So that's how we do it. And again, even if polar didn't really click for you last year, the curves that we deal with aren't going to really be that complicated. And the ideas are really more calculus ideas than they are, it's not about the taxonomy of limescence and witches of Agnesi or whatever they're all called. It's not about that at all. It's about thinking polar and using calculus that we already know to figure some of this stuff out. So there you have it.